Hello, welcome, and an excellent evening. And today I want to mix up things a little bit. We're doing another Let's Code video, but not for MS-DOS as we would usually do, or some assembly for MS-DOS, because usually we do C coding on MS-DOS, but this time I want to do something different, namely do some C coding on the Commodore PET. Yeah, you can also use the C64, and maybe I will do 2 or 3 videos on this. Not sure how far I will go because this is all very new to me as well. But the reason is that right next to me I have the Commodore 3016 PET, where I did a couple of videos in the past. You can search my channel for that, together with the Commodore 8050 disk drives. That I also did a video about some restoring, some repairing, but I'm not doing that much with the PET, and the reason being is there is not that much software that's very interesting, and I don't really know how to code for it. But then I found out that there is actually a very nice C compiler called Oscar 64 for the C64, but also for the PET and the VIC20. And the C64, the PET, and the VIC20 all use the MOS 6502 microprocessor. And we could do, of course, 6502 assembly, but I don't know how to do that at all, so I would need to learn that as well. And it is not super complicated because it's a very small processor. It would be probably very tedious, and there are a lot of videos already out there about 6502 coding. So I thought, why not do C programming? Because this is actually a very good C compiler. It does a lot of code optimizations. There is also a different C compiler called CC65, which targets even more machines and supports a lot of different things, but it doesn't compile to efficient code as well as Oscar 64. And Oscar is also being developed quite extensively. I figured out a bug in the PET standard library for Oscar 64, and it was fixed in like a day or something like that. So yeah, that's great. Insofar, I would love to do a few little things. And in this episode, I would first show you how to set up Oscar 64, because as far as I can tell, it is not included in Brew. It is not in the usual package managers because it's really niche. It lives on GitHub at Dr. Mortal Wombat and then Oscar 64. I will put a link to the repository in the video description, and I'm going to show you how to compile this on macOS. The same should work for all the Linux variants. For Windows, I would say you have to figure it out on your own, but maybe it's easiest to just install Windows Subsystem for Linux, WSL, and use Ubuntu or something under Windows to compile this. You don't need a lot of things. You need a C compiler or a C++ compiler. I'm not sure what it's written in. It's seemingly written in C++, so you need C++ compiler, which you have if you install the Xcode utilities. You need Git, and then you can clone the whole repository, and you can switch into the subdirectory Oscar64. And the next thing that you need to do is you need to create a bin and a build folder. Otherwise, the make system will fail. There's the make file in the subfolder make. So we tell the make utility to change to the make subdirectory, and there's a target called compiler. So once you've installed your C++ compiler, your make tool, etc. on macOS using the Xcode build tools, you will be able to call all of this, and On Linux, similar, you need to install make and clang, and I think, for example, on Ubuntu, I think it's Dev Essentials or something, some package like that. Yeah, you should be able to figure that one out, I hope. Then you can run the make tool, and it takes, I don't know, a minute or two, because, I mean, this compiler is very small. It has to target the 6502. So there's not that much that you need to do. Like CPU wise. Yeah, and it will take a minute or something. Pretty fast usually. So let's wait for this to finish, and we'll see how we can use the compiler. And I finished speaking, it was already done. So there we go. We now have a compiler in the bin folder, which you can see here. It has a couple of flags that you can pass. -I include path, which you usually set to the system libraries that OSCAR64 comes with. -O for the output program. -RT for the runtime that should be used, because there are different runtimes. For example, one with printf support, but printf takes up significant memory. So if you don't need printf, you can leave that out. TF for the target and TM for the machine. Not quite sure about TF, but TM, for example, will be set to PET for our cases. -E and -N, I'm not quite sure, but you have optimization flags from 0 to 3. You can compile with debug symbols. Yeah, and you can even create a D64 disk if you want to. I think, and yeah, give it the source file that you want to compile. So that's pretty simple. We will also put the bin folder into the path. So I'm gonna do something like $pwd, which gives you the current work directory, /bin, and then also $path. So this way we should be able to call OSCAR64 without any issues here. So that's very nice. That's good. Then we created a subfolder hello, where I put a hello world program that should be doable to compile. It's the standard C hello world program. We include the standard IO header, which gives us the definition for hello world. We're creating a main function which returns an integer as usual, and then do printf hello world \n. Let's see what happens to these characters, because character encodings are kind of an interesting topic, because the PET uses PETSCII, and here we store ASCII values basically, and then return. So maybe it will work, maybe we'll have an issue. Naively, you would think that you would just type OSCAR64TM equals PET and do something like output file should be something like hello. I don't know, something like that. Maybe .prg. And the input file will be hello.c. Let's see if that actually works. Seems to work fine. We can also do optimizations, for example. Also seems fine. And we get back a hello.asm, hello.int, whatever that is, .lbl, maybe label, a map, and a program. We can try to identify hello.prg, and currently it's only identified as a shared library. We can try to look inside of it. And yeah, it's not an ELF object or anything, it's just pure binary data. But we can already see that this program is 5 kilobytes in size, so whatever runtime was chosen, it is quite large. This is only a hello world, and it's already taking up 5 kilobytes of the precious 32 kilobytes that we have available. But maybe it will work. We will also have a look at the hello.asm in a second, which is 83 kilobytes, which is massive. I would guess that probably the library is already in there. I've already fired up the VIC PET emulator, XPET, which is quite a good emulator and which can do all kinds of hardware emulation like the 8050 disk drive, etc., etc. And I've already opened the Finder at this place, so let's drag and drop the hello.prg here. And as you can see, it seems that there is something happening, but the hello world looks very broken. And let's do the following. The PET usually doesn't have lowercase characters, so my guess is that we should probably put this into all caps. Let's compile it again. And let's also restart the program. We can probably do the same here. I'm not sure if this will actually reload the program. No, it will not. It's still the old file that is being emulated. So we just drag and drop the new thing. And lo and behold, we get hello, world, which is quite nice actually. And what we can also try to do is we can try to print some variables. For example, we will do a variable int I equals 1, 2, 3, and maybe something like a float variable, which should be, I don't know, like p13415 or something. And let's try to print those as well, like an unsigned integer and like a float. And do I, f here. All the warnings disappear. That's good. Let's compile it. Go back to PET and do the same here. Okay, hello world 1, 2, 3, 3.4145. Pretty neat, pretty neat. So that is actually a very nice thing that will work. And this is also why the program is that big, because printf is actually a pretty complex function. It seems very simple, but it is actually pretty complicated. We can have a look at the assembler code that it used. It's even commented a little bit. There's a startup which does all kinds of things. I'm not quite sure because I'm not good at 6502 assembly. The nice thing here is it actually writes the bytes plus the opcode name, and sometimes a couple of comments. Not sure if they're useful. The main function seems to return a 16-bit integer, probably. That's what it probably means. And we also saw that we actually return to basic, so that is pretty nice. Usually many of the PET and Commodore 64 programs just run until you turn off or reset the machine. They can't return to basic. This one can, which is quite useful. There is even the code for the printf function, which takes a unsigned 8-bit pointer and returns void. So this seems to be all the code for printf. And there's probably also the formatting of floating point variables, etc., etc. So that is basically all of the stuff here. You can see this is all still in the printf function. And there's not much else. There's some other utility functions called divmod32, uint16 to float, etc. Things like that. This seems to be everything from the standard library that they have, the C runtime. Yeah, there's a C runtime. For example, they have a function for probably a float multiply or something, I guess, because the 6502 doesn't have any multiply instructions, so I guess this is what this does. A lot of cool things happening here, and much of this is probably not even needed if we want to do very simple things. So I will give you another Hello World program, which is a bit more stupid, but also at the same time much smaller, and with which we can build much more interesting programs on the PET in later videos. So 1 second while I prepare this program. Let's do a little bit more direct access to the hardware. First of all, I've already included a bunch of things that we'll need. standard IO, standard library, etc. And something called con.io, which we already know from MS-DOS. This is not a standard library from ANSI or ISO-C, but this is a platform-dependent thing, and it stands for console IO, and gives us things like clear screen and similar things. For example, we're gonna end this program on a get character and clear screen to clean up after ourselves, which should be just fine. Also, we can turn off the text cursor because otherwise it will be kept blinking on the screen. And we will also do a clear screen beforehand, so we don't have any of the nasty stuff hanging around from the basic initialization, which is fine. Then we also define a pointer to the screen RAM memory, which is at 8000 hexadecimal. This is the pure frame buffer basically, and for the PET this is only characters, there's no color RAM or anything. It is 1000 characters in size because it's 40 by 25 for the PET that we are targeting, but there are different memory maps available for different PET machines. Also on the C64 it will be at a different location probably. You will have to look that up. But I'm going to tell you, for the PET 3016 and also I think for the PET 2000, the screen memory is at 8000 hexadecimal and it is 1000 characters in size. Then we'll have two functions called PETSCII to screen and convert buff, which we'll call PETSCII to screen, because all the character strings that we're using here will be PETSCII encoded, which is the default for Oscar 64. But the video RAM actually doesn't use PETSCII, it uses so-called screen codes. So this is something that is a different, yet another encoding, and we will just type down the function to convert between PETSCII and screen. And I think that's not in the standard library yet, so we'll do that in a minute. What I want to do with you is to have the hello world message jump randomly all over the screen. So first of all, we will do the screen itself. I will call it message 1, and it will simply be hello world, just like that. Then we'll have a message length, which is called message1_L for length, and this will just be the string length of our message. Fine, just simple enough. Then we'll have a timer, which we'll call start clock, which will be updated all the time, so we have a little delay, and it uses the internal timers of the PET, if there are any. I'm not sure how it's being done. Maybe it's just counting clock cycles, not sure. On the C64 you would have something like the time of day from the CIA chip to use basically, and that's also good. And we'll have two offsets into the screen memory called old destination, which is 0 at first, and new destination, which is randomly updated, where we'll print the hello world message. Very simple. And we do the text cursor, turn off, clear the screen, and yeah, then while we're not done, and we also need that as a variable at some point. Where do I put that? Probably here, unsigned character done equals 0, so it will be false initially. And we will do this loop until we're done. And the most simple thing here will be to set the start clock to the current clock value, and then we will do while the current clock minus the start clock is less than 25, which is maybe half a second, I think. I think this is updated like once a frame, if I remember correctly. So there are like 50 clock ticks on the PET per second. Then we do if a keyboard press was detected, then done equals 1, and we'll quit. This should already compile, and give us a blank screen until we press a key. So let's try that. There's no errors. Let's switch to the PET and execute the code. The screen goes blank, text cursor is turned off, and when I press a key, we jump back to basic. Perfect. Okay, we have basically our main program done, and we can reuse this for all kinds of effects and animations and stuff, I don't know, just like we did on the PC. Now, if we want to put something into screen memory, we could, for example, very simply do the following. We could just do memcopy to, let's also do new dest equals 0, so we have it initialized. We copy to new destination, screen plus new destination from message 1 with length message 1L. Let's do that and let's see how this looks. It will always write to the same thing, namely the very first byte in screen memory, which is fine. And as you can see, it looks like alien speech. I don't know. It's totally broken. That's because the PET characters have a different encoding compared to the screen characters. So we need to do our function PET to screen. And you can look up this encoding actually. I will just type it down. It's a bunch of if statements. If the character we pass in is greater than 0 and it's less than 32, we are returning the character plus 128, so it's shifted like that. And we should probably take the curly brace and put it here. Next case is the character is less than 64. Then we return the character itself. That's actually verbatim. If the character is less than 96, sorry, then we return the character minus 64. And if the character is less than 128, you see there are always like these blocks of 32 characters that are mapped to different screen codes. We return the character minus 32. And if the character is less than 160, we return the character plus 64. If we have the character less than 192, we return the character minus 64. Not sure if we can express this more easily, but I think that should do the trick. If the character is less than 255, not sure about 255, that's actually not covered, huh? Well, I think that's just the identity. We return character minus 128, and else we don't even need the else, we just return the character. All right. Sounds a little bit weird, the whole thing here, but that's actually how the screen codes are defined. And then we can just do for int I equals 0, I less than buff size, plus I. We loop over the whole string that we're getting passed, and we're doing buffer I is being replaced with PET to screen of buffer of I. So we override, we basically convert. So we need to convert this thing once. Basically what we can do here is call convert buffer message 1 of length message 1L. This will convert the buffer to screen codes, And we do have an error in line 46. Yes, okay. It's complaining about the const, I think, because that is obviously not happening, because the const is of course not allowed to be changed. So for this time being we will just make it a non-const thing. It's of course not very nice to cast away the constants, but it's just for converting, so we won't talk about this again. Let's quit this program and restart the newly done program, and there we go. Now we avoided the whole printf. We can also now switch to a different runtime which doesn't include the printf, which will make the program much smaller, but I haven't done this yet. For that we would need to choose a different runtime. We'll do that in a minute to optimize for size. Okay, so that's that, but we want to move around the message on the screen, so we will do something like new destination is random function, and we will end this with 1000, so we get only numbers from 0 to 1000 minus the string length, so we don't run over the end of the screen memory actually. And that we will use as the new destination, and we'll have to erase the old value, which we'll be doing before the memcopy, because we might overwrite the new message otherwise. So we will do screen old, screen plus old destination, comma, we'll print a space, which is actually the same in screen memory because of this block here. The characters up to 64 are actually the same, and 32 should be the space, I think, so we don't need to convert it. Message 1_L. So that should do the trick. Let's compile this. No error, that's good. And the finder gives us this here. Okay, we did something wrong. The memset didn't work. Screen plus old destination. Oh, yeah, of course, because I need to do something like old dest equals new dest. That should update, because before we were just erasing position 0. And let's run this program. There we go. Now we have hello world jumping around the screen. Very nice. And very fast this is. We can take out the clock actually. Just let us comment this out and we'll see how quickly the PET actually can execute code and write into screen memory, because it's amazingly fast. You see, there's so much screen tearing we can't really see what's happening. It's that fast. So you can do some actual very fast text-based animations using the PET and the Oscar C compiler. It's actually pretty impressive. So this is working. Let's have a look how large the program is. The program is currently 564 bytes. So as you can see, we don't even need to switch the runtime. The assembly file is still 8.8 kilobytes, which is much smaller than what we had before. So let's open it up, reread it. There's still a startup. There's the main function doing all kinds of stuff. It's calling the clock function, as it seems here, jump subroutine, hex 05CE. It's doing a seed for the random, I think. It's doing the memset, also subroutine. And we can see the different library functions here, like keyboard hit, memcopy, memset, very simple. And the clock function, which does not much. We could look up the memory map probably. It loads the accumulator with $8F. Is this an immediate or does it load from the memory location? I have no clue. As I said, no idea about the 6502 addressing modes. Store something at accumulator plus 0, 1, 2, and 3. Yeah, it does something. It does something. Interesting. Yeah, it's probably not that hard to understand if you know a little bit of 6502 assembly. But as you can see, the OSCAR compiler only includes that part of the runtime that is actually needed. So all in all, we have now a program that is not even 3 blocks in size, one block being 256 bytes. And it's already doing direct writes to screen memory. Very nice. And it even quits to BASIC afterwards. So yeah, that is our very first program for the Commodore PET. And you can run this on a real PET, of course. You can also switch to target machine C64 if you want, but then you would need, for example, different screen memory address looking at the memory map of the C64. I think the OSCAR 64 compiler is great if you don't know much about 6502 assembly as I do, but I can look up the memory map and see what the 0 page contains, where the hardware is, how to interact with the hardware directly, and use my C coding skills to do exactly that. And I think we can do a bunch of little programs over the next couple of episodes maybe to do some interesting stuff for this old machine. And I'm gonna try to film running this exact program also on the real hardware, so you can see in after this video how this is actually running on real hardware, which I think is the greatest thing that you can do with this compiler. But that's it for today. Thank you very much. Share, like, and subscribe. I hope to see you in the next one. Bye.